Hey, we finished this week with the very important limit laws. So we have a certain number of laws that allow us to um, put some limits together when we know them separately to form new limits. The first one is the sum law. So if you know the limit of f of x and the limit of g of x when x approaches c, then the limit of f of x plus g of x is just the sum of the limits. Okay, so example, let's take f of x equals x squared and g of x equals x and c equals 3. Then this law tells us that if you wanted to compute the limit of x squared plus x as x approaches 3, that will be the same as the limit of x squared as x approaches 3 plus the limit of x as x approaches 3. But as x approaches 3, x squared approaches 3 squared, which is 9, and x approaches 3. We already know that x approaching 3 by the fact that we're letting x go to 3 here. And then this together becomes 12. Okay, so that's the sum law. Now the constant multiple law tells us that if you have any number k and you're multiplying a function, then you can bring out the k out of the limit. So in one basic example, is given by, say, k equals 2 and f of x equals cosine of x and c equals 0. So what is the limit law of the constant multiple tell us? That the limit here when x approaches 0 of 2 times cosine of x is just 2 times the limit as x approaches 0 of cosine of x. But as x approaches 0, as we know from earlier courses, pre-calc, or even just algebra and trigonometry, cosine approaches 1. As x approaches 0, cosine of 0 is 1. So we get 2 times 1, which is just 2. And that's the limit, which we were able to compute using the limit law for the constant multiple. Excuse me. Now it's a product law, so now we have two functions instead of just a constant and a function. And to compute the limit of the product, if both limits of f of x and g of x exist when x approaches a certain constant, then we can take the product of the limits to compute the limit. Small example. Let's take f of x equals x, g of x equals e to the x, and c equals 2. So now the limit as x approaches 2 of x times e to the x will be equal to the limit of x as x approaches 2 times the limit, again as x approaches 2, of e of x, e to the x. And the limit of x, if x approaches 2, is just 2. And the limit of e to the x as x approaches 2 is e squared. So this is our limit, 2 times e squared. Okay. If you want, you can just forget about the dot there. Quotient law is almost the same as the product law. So if you want to compute the limit of a quotient, then you can just take the quotient of the limits, provided that both limits exist, and also that the limit of g of x is not equal to 0, as x approaches c. Otherwise, this expression will not be defined because you're dividing by 0, and we don't allow that. So take a look at one small example. So that suppose here f of x is just a constant 2, and g of x is x cubed, and c is 1. Then this rule tells us that the limit as x approaches 1 of 2 over x cubed is given by the quotient, the limit of 2 as x approaches 1, divided by the limit as x approaches 1 of x cubed. But as x approaches 1, well, 2 is just 2, no matter what, so we get 2 the top, and the bottom, as x approaches 1, x cubed approaches 1, so we end up with 2. That's our limit. Now we have a general limit law for powers and roots. So if n is a positive integer, then if you iterate the product law, you get the limit of f of x to the n is simply amounts to taking the limit of f of x as x approaches c and raising that to the n. And taking the square root, taking the nth root is the same. So basically you can bring the limit inside the nth root, provided that this limit is greater than or equal to 0, if n is even. We cannot take the square root of, say, -1. Right, so that's where this constraint here comes from. The limit of f of x has to be greater than or equal to 0. Similarly, we can also compute the limit of expressions where f of x is raised to a fraction. So if p and q are integers with q not equal to 0, then the limit of f of x to the p over q as x approaches c will just be a limit of f of x as x approaches c to the p over q, which is the expression here. And again, to be able to take the qth root of this expression, we need to assume that limit of f of x as x approaches c is greater than or equal to 0 if q is even, and that the limit of f of x as x approaches c is not equal to 0 if p over q is negative. Otherwise, we'll be dividing by something that is very small and thus becoming undefined as we try to take the limit. So one very quick example here is this example: f of x is equal to x plus 1 and equals 2 and c equals 0. Then this power law tells us that the limit of f of x squared, or the end, I'm just going to write on everything here just to make sure that we understand what we're doing. So inside the limit we have f of x to the n. n is equal to 2. So we'll just substitute everything here. Now, limit of, well, when x approaches c, but c here is 0. And f of x is x plus 1. That's f of x. And we're racing to n equals 2, so it's squared. And by the power rule, this is the same as the limit of x plus 1 as x approaches 0. All of that raised to the power 2. So we can bring the power outside. Here we don't face any problems. We're not raising to a fraction, and the power here is not negative, so we're not dividing by anything that is becoming potentially problematic. So nothing here is getting close to 0, and we're not dividing by anything like that. And so in fact, x plus 1 is getting closer and closer to 1 as x approaches 0, so we just get 1 here inside the parentheses. That's the limit of x plus 1, and we raise that to squared. We square that, and we just get 1. That's our limit in the end. And that is the end of section 2.3. So that's a wrap for the week. So we'll continue next time with sections 2.4 and so on. We'll try to, now when we take in things slow, but next week we'll try to move faster and faster as we become more used to dealing with algebraic expressions, just to get to a more computational part of the course, which is the active part where we actually get our hands dirty when trying to implement the techniques and apply the tools that we'll be learning, and apply to more specific examples, and perhaps a little bit more complicated each time. So okay, so that's it for this week.